Okay, so in this video, I'm going to show you how the LU factorization can be used to solve a linear system AX equals B. Okay, so suppose we have a matrix A and that we have the LU factorization for it. Then we can take A and replace it with LU in this equation and write LU x equals B. Okay, and so what I'm going to do now is I'm going to say, well, let for now, ux equal some vector c that is unknown. Okay, we can basically turn solving this linear system ax equals b into a two-step process with the LU factorization. Okay, and I'll explain later why we might want to do that. So as a first step, so step one is to solve the system. So I've let ux equal c, and if I substitute that into here, I get a system LC equals b. Okay, c is the unknown here, and we can solve it. And we solve this, so L is, remember, it's lower triangular, and we can actually solve it using what we can call forward substitution. Okay, it's actually pretty easy to solve this system. So we solve it using forward substitution. In any case, it's a substitution type process that is just plugging things in, and you'll see that you'll be able to solve for the first entry of this vector c by inspection, and then just substitute in to find c2, c3, and so on. Once we have solved for c, well, ultimately we want to find x. And so what we do with that vector c is we solve ux equals c. So we solve ux equals c. And we're solving it for x. Okay. Now we use back substitution. I mean, u is upper triangular, and that's what we've done in the past, is we've taken upper triangular systems and we've solved them using back substitution. Okay. So as an example, I'll take a matrix from a previous video that we've found the LU factorization for. So I'll say, let's solve the system that looks like this. So here's the matrix A, and we want to set this equal to minus 2, minus 4. So here's a system of the form AX equals B, and here is A. And if you recall, we factored A into the LU decomposition where L was 1, 0, minus 2, 1. Okay, so this is L. And U was 1, minus 3, 0, and 4. Okay. We actually found the LDU decomposition, but we don't need that here. We're just dealing with the LU factorization. All right. So this is U. So now we go to our steps. First step is to solve LC equals B. So I'll write that down. So step one. So L is here. C is unknown. So C is kind of like this middleman intermediate vector that we need to solve for that isn't really the solution to the problem, but it helps us get to the solution to the problem. And so I set this equal to B, and so B is here, minus 2, minus 4. And this is easily solved by forward substitution. I mean, the first row says C1 equals minus 2. Okay? So C1 equals minus 2. And then once we know C1, we plug it into the next equation, represented by the second row of this matrix equation. And if I plug in minus 2 in for C1, we can solve for C2. Okay? And it turns out that C2 is, C2 should be minus 8. Okay? And so we have our C vector. It's minus 2 minus 8. Okay? And now I can use that to solve the system Ux equals C. So we found C as the vector minus 2 minus 8. And now we move on to step 2. Okay. And step 2 is now solving Ux equals C. And so U is our upper triangular matrix that looks like this. X is the unknown that we are really trying to find. Okay? And we set this equal to C. That looks like that. And here it's the backward substitution. And so we can solve for x2 rather easily. x2, so that equation down there gives us x2 is minus 2. And if I do this backward substitution and look at the first row, it looks like, so if I plug in x2, I get 6 on the left. I subtract 6 from both sides. It looks like x1 is going to be minus 8. So our solution x is equal to minus 8 minus 2. Okay, the fact that these are just the entries of C switched, that's just a coincidence. But this is the solution to our system AX equals B. Now, as far as why would we want to use this as opposed to some other method, for instance, we could actually solve for x by finding the inverse of A and using x equals A inverse B, okay? But what I mentioned in class was that finding A inverse takes on the order of n cubed operations for an n by n matrix, okay? It turns out that doing either forward substitution or backward substitution takes on the order of n squared operations, okay, which is much better. Means it takes less time to do forward substitution and back substitution as opposed to finding an inverse. Okay, so that's why we would want to use the LU factorization. And there's a little bit more to the story than just that. For instance, finding the LU factorization actually requires Gaussian elimination, right? Which is on the order of n cubed. But if we wanted to solve multiple systems, that is, if we wanted to solve AX sub I equals B sub I for a number of systems, then LU factorization becomes much more attractive than finding an inverse because all we need are n squared operations to do the forward and backward substitution.